Kia ora koutou, I'm John Hosking, Dean of Science here at the University of Auckland, Waipapa Taumata Rawa. And it's a great pleasure to welcome you to the inaugural lecture of Professor Craig Radford. Craig was born in Taranaki and spent many holidays as a kid in, on or near the ocean. Mainly with his grandfather on the Taranaki coast, owes his fascination and love for the ocean to him. He started his university studies with a BSc in biology from Waikato, a master's in zoology from Canterbury, worked as a technician at Massey before doing a PhD here at Auckland in marine science. He was clearly looking for the right Super Rugby team to follow. After a couple of postdocs here, he became a senior lecturer, an associate professor, and now a professor, which we're celebrating tonight. Craig works in marine science. In particular, he is a sensory ecologist who specialises in how marine animals hear and utilise sound and how those animals are affected by human-generated sound. Many marine animals, such as mammals, fish and crustaceans, rely on sound for successful life history strategies, from mate selection and finding food to sound providing a cue for selecting a place to live. Craig uses a multi-disciplinary approach, including physics, physiology and behaviour, to tackle some of his important research questions. Tonight he will describe some of the highlights of his academic journey to date. Craig, the floor is yours.
It's kind of funny how you can stand up here and give a lecture and not be nervous, but I'm shaking tonight. So this is a motto that I've used many a time for many a funding application, and I think it's a classic one that everyone can relate to, and tonight I'm going to dispel that. So straight to the punchline. So in between my breaths here diving, you can hear the clicks of these little fish, and these are not the only animals that make sound in our oceans, but it's clearly a noisy place, and Jacques Cousteau, famous explorer, got this wrong. So I thought I'd get to the punchline first before I bore you with a whole lot of other stuff. So where did it all start? Well, in high school, I watched the Top Gun movie, and all I wanted to be was Maverick and 5 fighter jets. So I applied to the Air Force, and I'll get to that, but in the reality I went from the sky to underwater, and it's kind of where I spend a lot of my time now. Well, not so much now, but I did when I was able to get out there. So growing up, as John mentioned, I spent a lot of time on the coast down in Taranaki. This is one of our family camping trips. My mum's here. That's me trying to get a suntan. And all my cousins and my uncle. My grandfather's not in this picture, but spent a lot of time fishing. I'm not too proud of this now that I've embarked on the career that I have. But these blue sharks were eating out of our burley pot and eating snapper that we're pulling up, and we hooked them and they got their comeuppance, unfortunately. So that's something I'm not too proud of. And again, not too much has changed. I still spend a lot of time out on the water, and I still work on sharks, and I still have sharks. But let's go on to the good of science. These ones actually come from the tuna longline fishery, so I'm making use of the bycatch of animals that have already been sacrificed. So, as John mentioned, my grandfather, so this is him in the middle here. That's me, very young dad. That's four generations. My dad here on my left, grandfather in the middle, me and my son Noah, who's here today. and it's strange things happen because of the trajectory I had when I was at high school and wanting to be in the Air Force. I actually applied, I got in, and for some reason I never went. And it wasn't until my grandfather passed away probably 8 years ago now that I got the phone call from my parents, and it was a nice day, and I went and sat out on the deck at Lee, and I just kind of contemplated things, and that's when it suddenly hit me with thinking about him and the times I had with him, and being on the banks of the Inaugural River down in Taranaki, whitebaiting the Inaugural River, Mokau, Awakino, all those rivers, trying to catch whitebait, out on the boat catching fish, and it's in those moments that you realise how much a person kind of inflicts on your life and kind of what you get out of that. So, so I owe a lot of my love for the ocean to Grandad, and I thank him for that. So, as I mentioned, Noah, he's only about 2 months old there. He's now turned into this. He thinks, and my good friend Sean and Maria, I think they were there that night, he thinks he can keep up with drinking with me, and there's a 6 months later when he thought he'd got a bit better and could do it again. In terms of my career, I owe a huge amount to these three gentlemen here, and specifically Andrew and John. I was doing my Masters at Canterbury, and that's where I first met Andrew. He was supplying me with lobsters. I was doing a bit of physiology, respiration physiology on them. And I'd started at Massey University, and I was working at the vet school under John's predecessor, actually, Grant Guilford, and I was doing a lot of horrible things to large animals. You can imagine what goes on down at the vet school, and I was kind of sick of it, and I wanted to get back to my love of marine animals, and I just emailed Andrew out of the blue to see what he had on offer, and he had this underwater sound project which a student had just bailed on them. So I was like, underwater sound, knew nothing about it, didn't let them know anything about that, but I was like, yeah, keen, and and they took a huge gamble, right? I had a little baby, and I embarked on this journey on a PhD with them, and I owe them a huge amount, and they've been a great support throughout my career, and I'd like to think, well, I know we're good friends today, and it's great to have you both here. And this other person here is Chris Tyndall. He was HOD of physics at the time, so he had the pleasure of teaching a biologist physics, and he was a very patient man. I learnt a huge amount off him, and he was a huge reason why the project that we embarked on with this was a success. These are actually a couple of pictures. This one was at a Royal Society event. I won an award, so we got to dress up in penguin suits and go to this fancy dinner for which we all received our awards. And this is an image from Lizard Island where Andrew and Jenny and I spent a bit of time. And Andrew, I think Jenny took this photo. She sent it to me today, so I was good check at it. Andrew looks very surprised. So how do you know you've made it? So I don't know where I received this picture from. I'm not sure if you sent it to me, John, or whether it was Dave Bodsnick, but or it might have been Art Popper even. But I had it on my computer, and I was like, and when I was thinking about the presentation and what to present today. So this is an image. Was it Moat or was it Scripps? Do you remember?
I have to go back.
But this was the who's who, basically, of the herring world and sensory ecology and fish. There's a young strapping John Montgomery. I think this is 19 must have been 1988 that there was a book I think you guys were part of, and there's a whole lot of other people. So when you start to be invited to retirement events as kind of young, well, not John's not so young there, but young up-and-coming scientists instead of, I think that's when you know you made it. And there's a whole bunch of these people who are a lot older in this picture here, including this gentleman here, Bill Tavoga. I think he was about 92. And this wasn't a retirement event for Art Popper, who's had 3 more retirement events since since this one. And I was in a meeting with him the other day, and he actually said this is his last year. But I think he says that every year. So my collaborators, they're a huge part of where I'm at and what we've accomplished together. I say we've because it's a collective. It's just not me working alone. I first met Dennis back in 2009. So Dennis is this guy here. This was actually taken recently, so we're still working together out on the Gulf. And my track to where I got was a little bit unusual in that my personal life kind of dictated that I needed to stay in New Zealand and not embark on the big, postdoc adventure that most people did. So I was lucky enough that I won a few fellowships that allowed me to go overseas to work with some very cool people who are good mates of mine now, and we still do a lot of work together. So Dennis and I met 2009. He and Al I met so Dennis is from the middle of Canada. Strange to have a marine scientist in the middle of Canada, but there you go. And Al, he's in the middle of America, but he does a lot of work in Woodsole, so I've spent a lot of time up there with Al. And they've basically taught me all I need to know about the physiology work that we do now. And then Cara, who actually we did our PhDs together under John's tutelage, and we were lucky enough to secure a Marsden together a few years ago, which allowed us to embark on a shark herring project, which was a great success, which I'll present some stuff from that a little bit further on. And then more locally, I work with these wonderful women. Rochelle, I was thinking about this today when I was kind of preparing. I think it's about 10 years now we've been, wherever she is, we've been working together. And my first PhD student as the primary supervisor was with Rochelle as the co-supervisor, and we've done a lot of cool stuff. And more recently, with Fred and Jamie, again, lucky enough to secure a Marsden, and we're doing some pretty cool stuff at the moment on crustacean herring. And then there's Rachel, who's we're trying to embark on combining acoustics and statistics, which is no easy feat, but it's going to lead to some pretty cool stuff once we get it going. And then I don't think the technicians and stuff get enough credit for the amount of work that they put in and help us with, and particularly with our students and what we actually do at Lee. And I don't have pictures of many of them, but I do have this picture recently. John Atkins, who's no longer with us, but I still work with him very closely. No, I meant no longer at Lee with us. But and Jimmy, Brady, the workshop guys, Murray. I'm sure Jimmy always rolls his eyes when I walk into his office because I come up with some crazy ideas, and these guys always come up with ways in which we can do those crazy ideas. So without their help, I wouldn't be able to do half the things I do. And particularly John, right? John has kind of he hasn't kind of. He's revolutionised how we record sound underwater, and this is an example of what I did my PhD with. These old homemade jobs, where we kind of put an acoustic recorder in what we thought was a waterproof container. And, electronics and water don't go hand in hand. So John is a real genius, and we've gone from these types of devices to really nice, affordable, very capable instruments. It's just another example. Here's Brady. This is the old Hawari. We've got these monstrous devices that I was doing my PhD with. We actually this was a computer that we waterproofed in some canisters, and we're recording, and this is the type of system that was doing the same job now. So without this expert capabilities, I wouldn't be able to do half the stuff that I've actually been able to do. And then just getting to the last of my thanks, and then I'll get into a bit of the science. Goes to the many students that have been working with us. Jenny I'd actually just got back from the UK. This was back when we got about $6,000 to hand in our thesis on time, which I thought was very generous of the university. So it funded me a 4-month trip to Europe. And so I then got an email from John saying that we'd got some money, and I then had a postdoc. And so I come back, and Andrew had organised Jenny for us, unknown to me. So Jenny was the first student that I co-supervised with Andrew, and this man here, Shah, was the first one I co-supervised with John, and then Roz here was my first as a primary supervisor, with Rochelle as the co-supervisor. And then we all had the dreaded COVID Zoom meetings. These are a few of the students that suffered through that, who have all gone on to graduate or nearly graduate, and they coped, and they did a wonderful job with what they did. And then all of a sudden you get a bit older, and you start meeting them at meetings, and this is one that I don't know what happened to my hair, but this was in the Netherlands, and Matt was another student I co-supervised with Andrew. But it's good to see when you start, and then all of a sudden your students evolve, and they also embark on their own careers. So, the science. So our world is getting noisier. We know that. As soon as we step outside here, we hear the traffic outside. We go to the airport, you hear planes flying around. You go near factories, rush hour. It's a well-known fact that the world is getting noisier. And this is the same thing underwater. We're starting to explore the ocean more, trying to take advantage of it to harness its energy. But all our man-made advances in the ocean are actually creating noise, which can have tremendous effects on the animals that live there. And it's only really recently, when I say recently, the last kind of 40 years, that we've begun to understand how important sound is to animals outside the marine mammals. I'm talking about the fish and the little crustaceans and the invertebrates. And that becomes a problem when you understand the biology of the animal and the ecology when it comes to sound. And if we put noise into their world, all of a sudden they've got to find ways to deal with it where they hadn't used to be able to do that. So one of my key question what my group does is to understand the effects of noise on aquatic life. I got dragged into the marine mammal world with Rochelle, so I do some stuff on that. But my main animals are the fish and the crustaceans, and I take a three-prong approach with that. I try and understand the physics, and before we can even understand what the animals use the sound for, we need to understand what the acoustic environment sounds like that the animals are living in. So to do that, we understand the soundscapes. By soundscape, I mean just the ambient noise around the animals that they're focusing on every day. We want to understand who makes those sounds, and then we also want to understand how that sound propagates, because that's going to be different depending on a lot of different things. And then we need to understand the physiology and morphology. What are the sound detection structures in these animals? How sensitive are they? And then lastly, we're interested in the behaviour and the ecology. So what types of behaviours are mediated by these sounds? What are they using these sounds for? So now I've just got a few examples of different aspects of these questions that we've been tackling. So starting with the acoustics, I've been lucky enough to record from many different locations around the world, and this is just an example of where I have recordings from. So obviously I've got a bunch around here from New Zealand, basically from the Kermadec Islands right down to Campbell Island. Not so many around Australia, but up on the GBR on the Great Barrier Reef. I was lucky enough to go to Malaysia with Shah, so we did a bunch there, and then just through my collaborations around the rest of the world. So we have a pretty good record of many aspects of what the underwater environment sounds like, even up in these Arctic lakes in Canada. So I spend a lot of time, well I used to, now it's all my students, but we spend a lot of time just listening to the ambient environment and trying to figure out what is, this is so low, does it pop up? So this is a recording that Lucy actually put together, Van Oostrum, of Rangitahua, the Kermadecs. These are just some examples of what the ambient environment sounds like up there. So I'll just play this. So we actually know that those fish produce those sounds. So you could understand that that was just a whole lot of recordings put together. That wasn't just one recording that we had all these sounds in. So you can spend a lot of time just listening to the ambient crackle of what's happening. And a lot of the time we don't actually know what is producing those sounds. Here in temperate environments, we only know a small fraction of the animals that could potentially produce those sounds. And a lot of the stuff that we hear, like in those examples there was only one particular fish that we think produced that sound, and that was because it was similar to a species that we know of here, the big eye. There's a species that are very similar up there, so we're just making an assumption that it's that. But without the proof of recording the sounds in a tank, it's very hard to attribute specific sounds to specific animals without that proof. So we do a lot of guess that animal sound. So I've got a few recordings here. Andrew and John and Jenny might know these, Selwyn, but we'll see if you can guess what these are. Anyone has a guess? Gernard? I think I heard it. John Dory, yeah. Then, what's this one? Where's that? Ashley. It's our native paddle crab. So these guys are. This is a pretty cool story actually. So we had a bunch of these. I think Tony Hickey used to run a lab with them, and I think there were a bunch in a tank at Lee, and Ashley was actually down there one day, and she heard this sound. She wasn't actually going to work on this, but she was like, "Hey, these crabs are making these crazy sounds." So we're like, and we jumped on it. So they make this sound as an aggressive movement towards a mating pair, and it's made by a male crab trying to get a receptive female off another male that's already claimed her. So this guy, this recording goes for ages. So you probably don't know this one. This is a toadfish. So this is a fish that I work on in the US, and there's several different species around there, but there was a famous story in the San Francisco Times where these guys were actually keeping houseboat owners up during the summer months because they can produce this sound for hours on end. We've had one in a tank go for an hour and a half, just and and what they're doing with the sound is they're trying to attract a female into the nest to lay eggs so they can fertilise them. So this is another, probably not many of you know this, this is two-spot demoiselle. So we're not sure why they produce this sound, but it's quite a common one on our reefs. Hayley, you'll get this one. It's the gurnard. So that's spiny lobster. We're pretty sure that that's produced by the gastric teeth in the stomach. And then the last one here. So that's the sea urchin. So these guys are responsible for the huge dawn and dusk chorus that we hear on our temperate reefs. So you can imagine a lot of what happens is there's a lot of guesswork and we hear lots of funky sounds, and it's quite serendipitous about how we figure out what animals are actually producing those sounds. How do boats influence the soundscape? So this is some work by Louise Wilson, and what we were trying to do is it's a lot easier to understand how large ships produce sounds. They have tracking systems in them, and we can track where they go, and we know where we record and what time they come past. But what we don't know is about small recreational boats, and this becomes important for places like the Hauraki Gulf, where pretty much 1 in 10 people in Auckland own a boat. They're always out on the Gulf, and all of a sudden you've got rush hour traffic on a nice sunny day underwater. And what she was trying to do is understand what that contribution to noise was by these boats. So these figures here, this is just frequency on the x-axis, intensity level on the y-axis. My right-hand side is spectral profiles of locations with boats, and this is the same location without the boats. And you can just visually see what the boats do to that soundscape. The low frequency, kind of below 1,000 hertz, is where the large majority of the fish and crustaceans make sound from what you just heard. And you can see that the frequency that the boats produce are in that same band and increase that part of the soundscape. And that becomes important in terms of masking. These boats are producing sound in the same frequency band, therefore it's going to make the animals a lot harder for the animals to communicate. You can think of it more as as the cocktail party effect, if you like. If you're at a good party and it's loud, you have to be closer together in order to talk to each other, compared to if, say, you're at a boring party and it's not so fun. Then you can kind of yell at each other from either side of the room. Moving into the physiology aspect of this, a lot of the work that we've done is looking at the hearing structures and looking at the variation that we have within different animal groups. And a lot of this requires collecting dead animals, and that's where the fisheries becomes really quite a good source for us, because we can go there and we can collect lots of bycatch animals. As long as they know we need them, they're very good at keeping them on ice so we can actually use them. So this is some work that Derek Sauer did, and this was with the collaboration with Cara, where we're looking at the ears of sharks. So here we've got 6 different species. We've got school shark, smooth hound or rig, so this is the typical one you get in fish and chips. That's mako, hammerhead, a carpet shark, and then a thresher shark. And you can just see by just looking at those structures, there is a remarkable amount of variation in the shape of these structures, which might then relate back to their ability to hear. These are just gross dissections. When you pull these things out of the head, you don't really know the orientation of them in the head, and that's where we took advantage of medical imaging. Here we have on my left, we've got some MRI imaging, so magnetic resonant imaging of 4 species, and this technology allows us to put the entire head into the scanner, and we can image the ear in situ, and then we can make reconstructions. So we actually know the actual orientation inside the animal's head. And something that we're working on now with Lucille and Cara is using micro-CT imaging, where it provides a much higher resolution and we can get some pretty cool images. This is a recent one that Lucille did of a hammerhead. You can see the brain here, the big optic nerve going out to the eye, and this is the ear here. So by doing this, we can then co-register, so we can combine the MRI and the micro-CT images, and we can get a much more detailed image of how the ears are situated in the head and what they actually look like. And then we can start doing some modelling on this to see how they respond to sound fields. We're also doing similar things with crustaceans. This is a snapping shrimp brain, and you can see that we can get some quite good detail out. So this is hot off the press. This is just recently done. We've just recently submitted the paper, and we can reconstruct the different structures and work out what they look like and what that might influence with their sensory systems. Then we're also looking at how well they can actually hear. We know they have the sensory structures. We know that they can detect sound, because there's a lot of anecdotal evidence that different species respond to sound. And so we set up these what we call auditory evoked potentials. So this is a technique that is still used on infants. So it's a technique that was used in medical science, where basically you just put little electrodes on the head, play the sounds, and then you can measure what the brain is responding to. So this is a setup that Carolyn made for looking at sharks. And just have a speaker, you have the animal tethered to some device, you have the electrodes on their head, and you can play different sounds and you can measure the brain. So where you start to see what we term an auditory threshold is the first time you start to see a response in the brainwave. So here we're going from, down the bottom here, we're going from low frequency to high frequency, and you can see as the sound gets louder, you start to see a response from the brain, and where you first start to see this is what we term our auditory threshold. So we've been able to do this for a range of animals. These are some audiograms from sharks. We got sound pressure level on the y-axis here, just frequency across the x, and 3 different species. Don't worry about the different lines. But what this is showing is that the different species, they have the same similar shape in terms of this classic U shape, but the bandwidth at which they hear over is different. And this could be related back to the morphology of the hair structures. We have some other information associated with this that I haven't presented in terms of hair cells. So there's lots of correlates that we can kind of figure out to why we're starting to see, why we see these big variations in hearing structures within just these 3 groups of sharks. We've also been able to record from crabs. Again, this is just an information slide. Don't worry too much about the lines, but that you can just see from the shapes and the bandwidth that just between these 4 different species of crabs that there's a huge amount of variability in there and what they can actually hear and how sensitive they are to sound. So moving into the behaviour. We know that we know a bit about the underwater soundscape. We know how well and the machinery that the animals use to hear. But what does that mean for the behaviour and the ecology of the animal? So this is some work Lucy Van Oostrum did for a MSc looking at big eyes. So this is kind of my model organism here. We know a lot about the big eye. We know how well they hear. We know about the sounds that they produce. But Lucy came on board and she wanted to find out what that sound is used for. These particular fish are planktivores. They live in caves during the day, as I showed in that first image. And then they come out on top of the reef at night to feed. So we were thinking that maybe this is used as a contact call. So a contact call is something that animals use to maintain group cohesion. You know, monkeys use them when they're scrambling around in the trees. Elephants use them. Dolphins, some species of whales. And it's a behaviour that's quite often associated with higher order vertebrates in mammals. So we were thinking maybe this is something that evolved early on in the fish, and it had been proposed before, and we were like, well, let's give it a crack. So we went out, got a bunch of fish, put them in tanks, and you can see we have a little speaker down here. Here's our sound trap hydrophone, and what we were doing is the fish were behaving as naturally as they could in the tanks. They were producing sound, and all we did was we made that environment louder, and we watched what happened to the school of fish. If our hypothesis was right and that they are using it as a contact call, as soon as we turn the sound on, you would see that the school of fish would get smaller. They would be closer together. Because it's noisier, they need to be closer together in order to be heard. And here are a couple of the photos that we took, and you can see that when the sound is off, I've just put a polygon around this, and you can see that the school is quite spread apart. You turn the sound on, and all of a sudden they become tighter together. So what we did there was we basically provided the first evidence that the contact calls were used in early vertebrate animals. This is some more recent work that Sophie's currently doing for her MSc. We're interested in this black angelfish. I've been interested in for a while. We know that they produce sound. They have this very cool behaviour where this is a nest, this is a male fish. These are a bunch of eggs. So the female comes in, lays the eggs in this nest, and the male then fertilises them. And I was interested in what they're using this sound for, because quite often when you go diving, you swim up to these guys and they'll swim at you and they make their sound. So it's some type of scare tactic, some type of scare tactic to shoo fish. And if you observe them, they chase a lot of fish away from their nest to stop them eating the eggs. And we thought maybe it's also used in a reproductive context. Can't find the play button here. Here we go. So here's a female coming in. They do a little dance, and then in this particular example, he chases her off. So there are other examples that we have where the female, they'll do that little dance thing side by side, that little wiggle. The male will produce the sound, and then the female will start to lay eggs on the nest. So that's the third part of the story. So then how does noise affect animals? It can affect animals in different ways. And in this cartoon here, if it's very loud, so we've got two variables. We've got decreasing source level, so the sound gets quieter, and then we've got increasing distance from the source. So effectively the sound gets quieter because you move further away. If the fish is really close to the source and it's really loud, it can have potential injury, and sometimes that injury is death. And then there's potential effects on their hearing as you get further away, as the sound gets less, where you can have permanent threshold shifts, PTS, or you can have temporary threshold shifts. The temporary threshold shifts means your hearing returns. And this outside area is where I'm more interested in. How does this affect the behaviour of the animal, and how does this disrupt their communication by masking? So by understanding what the soundscape sounds like, understanding their hearing abilities, and then understanding their behaviour, we can start to combine these three things and make some inferences and do some modelling to figure out how that might affect their active listening space, if you like. So this is an example from Ros, where she's working with the large ships. Don't worry too much about this. I've got a summary cartoon in a sec. But this is basically as the ship approaches, these lines at the top, and this is what the sound profile of the ambient environment does. So as the ship approaches, gets to its closest point, and it gets loud. So what we do with the modelling, we can model the propagation of that sound, and we can include in our model their hearing ability, and then we can work out how that sound might affect these particular animals as the ship approaches. We're using two examples. We got a marine mammal example in the form of a Brutus whale, and then we've got our big eye fish example here. So we obviously don't have hearing data from the Brutus whales, but there is some modelled data about how well, what their potential hearing could be. You add in the ship information, and what we have up here is what their communication space or listening space is without any ship sound, and you can see the size of the circle is representative of the distance that they could detect that sound over. You add the ship in, and you can see that the communication space shrinks down to a really small difference. And our modelling of this scenario suggests that the 99% of the communication space can be lost as the ship passes by them. So it's quite significant. More recently, we've been interested in the small boats. This is going back to Louisa's stuff. What we have here is Goat Island. We got two different scenarios. We got daytime and we got nighttime. So what we did here, we did a similar situation where we modelled the sound field. We're using the big eye fish here as our model organism. We know about their hearing ability, and we know about the soundscape in this environment. During the day, Goat Island has gotten really noisy, and that's because of the fish making the sound, and there's lots of biological activity during the day as accompanied by the boats. At night time the boats tend to disappear and our ambient environment gets quieter. So what you're seeing here is that the effect on the listening space, because our ambient environment is louder during the day, we don't have such a decrease in the active listening space of these animals during the day because the environment's already loud. What we're seeing here is a big effect during the night. Because the ambient environment's quieter, any particular noise that comes in there is going to have a greater effect at reducing the ambient space of these animals during this time. And that's particularly important for the big eye, right? Because as I mentioned, these guys are planktivores. They come out and they feed at night, and they're most active at night, and their communication space is going to be significantly affected at night by boats coming into this particular habitat, as opposed to during the day when they're in the caves and they're not particularly interested in what's happening outside. So when we combine all this information, and I think that's the beauty of this multidisciplinary approach, is that when you combine them all, you can get a really good overarching story about the potential effects. We're not just looking at one isolated instance or one isolated effect on a particular variable. We're combining it all to make a bigger difference. So, enough of the science. So the things I've learned, as I just mentioned, this multidisciplinary approach is what I think is critical. Because you're combining different frameworks, you're not just getting isolated in a particular aspect, and you're getting more of a holistic understanding of what's actually happening to these animals. And teamwork makes for dream work. Without my collaborators and the various people that I work with, as I said at the start, none of this would have been possible. Something that I've learned more recently is that talking to different people who see things differently to what you do. So more recently I've taken advantage of the friendships I've made with some of the local fishers, and talking to them about what they see when they're out on the water every day. These guys and ladies have a real understanding, because they're out there every day, they have a real understanding of what actually could be potentially happening, and they're seeing real world problems. And more importantly, it's not about us, it's about the environment and the animals. Quite often we get caught up thinking about how is this going to affect us, when really it's not how it's going to affect us, it's how it's going to affect the animals and the environment in which they live in. And lastly, to wrap it up, I just want to say thanks to the many amazing people that I've had the chance to work with, the cool animals that I've had the opportunity to work with, and to the people that I still am working with. So thank you very much.